looking at projectile motion today. The big ideas here is that we want to look at the fundamentals of projectile motion, what happens in the x and y directions, and use some kind of common sense extrapolations of that allow us to solve complex projectile motion problems. So our basic scenario that I want to think about briefly is if you imagine throwing a ball up and down, basically doing the free fall scenario, and then you throw a second ball, B, in an arc. This is a projectile. It moves in both the x and the y direction. Which of these will be in the air longer? And if you look at these two, they go up to the same maximum height, which has a greater initial velocity. And what determines that? Which one will have the longer time in the air? So I would take a moment, think about that, maybe write down those answers for yourselves and see if we can reveal that as we go. There's a device that we can use to kind of think about looking at projectiles, and we sometimes call it a dropper launcher. It has other names, but it's a device that allows you to drop an object straight down, free fall, and launch a horizontal projectile. And so we're going to look at what this looks like, and we might ask ourselves, what if we used a really high-speed projectile? There's a very famous idea of if you did something as fast as even a bullet shot from a gun, or a cannonball or something very, very high speed, and at the same moment you were able to drop one of those projectiles, would they hit the ground at the same or a different time? More on that later. So here's the video. We can watch. This is just an example. This is a pretty large scale one. It uses, I think, billiard balls, from a pool table or something, drilled out. But it's a spring-loaded mechanism where you can put a ball with a hole in it, and then the pin gets pulled out of it. It will drop straight down. And then if you place a ball on the other side, when you release the thing, it gets knocked horizontally. And so if you watch the demo, the setup will be that both balls are placed on there at the same time, and you can watch them both fall. Well, one fall and one be launched, and you should see they hit the ground at the same time, even though they took different paths. And so one of the things that we start to learn about projectiles is that the y component of the projectile's path is really the same as just a free fall path. And so this is a high-speed camera shot where a bunch of pictures were taken very, very quickly as something fell. And you can see that for every place that the red ball that was dropped straight down, how far it's fallen is the same distance the yellow ball has fallen as a projectile, even though it's moving in two dimensions. We can kind of go through this in a little bit more detail. Here is the free fall path number one, and then we've got our projectile path. So I'm going to overlay on this. We've already got the gray of our projectile path. The gravity-free path, which is constant velocity. And so if we think about where it is, if it starts here, and then it just keeps going at a constant speed, a constant velocity, and covers the same amount of distance every second, right? Equally spaced. This is like rolling a ball across a table, no friction. On the other hand, if we were to drop a ball straight down the free fall path, right? These blue marks, it gets further and further every second, right? It goes 5 meters in the first second, then 20 meters after 2, and so on and so forth. But if you put those together, that will give you the position of our projectile. Now we could go a little bit further and we could say, well, I don't just want to know, how far it's traveled. I want to know how fast it's also going. And so we can start with the given information. If we say that the x velocity initially is 30 meters per second, well, that's never going to change because in the x direction, it's a constant velocity. That's kind of one of the fundamentals here. The y velocity can also be tracked. But while we're looking at x, you say, well, the initial x position is 0, and every second goes another 30 meters. So it goes 30, 60, 90, 120. If we look in the y direction, the initial y velocity is 0 meters per second. After 1 second, it's -10. After 2, -20. After 3, -30. And after 4, -40 meters per second. We can go ahead and use our free fall equations. 0 meters, -5 meters, -20 meters, -45, and -80 meters. That's Not that surprising. And then we can find the total velocity by using the Pythagorean theorem, the y component squared plus the x component squared, take the square root to find the total velocity, which starts at 30 meters per second, ends up around 32, then 36, then 42, and finally 50 meters per second after 4 seconds. So we could actually overlay all of that on top of our path and see that the velocity vector for the x direction is constant. The velocity vector for the y is getting bigger and bigger. And if you were to combine them together, you would get this kind of in the teal color, this greenish, the total velocity vectors. We can talk about the equations that actually come from this. In the x direction, we have constant velocity motion. So we barely need to do anything. And in the y direction, we have constant acceleration, and we already have solved that problem. So we get x final is vxt, vx is a constant. In the y direction, you get our full kinematics equation, but we've replaced x's with y's, and v with vy, and a with g, because the acceleration is due to gravity, and we get those 3 equations. Now, there's a lot to play around with here. We started with just a horizontal projectile, but you can launch a projectile at any angle. This is a great simulation. You can play around with it, see how projectiles go as you do it. I want to go through an example here of what if a projectile were launched at an angle. And so this is from packet number 2, page 15, if you want to kind of fill it in and follow along. We're told that the initial velocity is 50 meters per second at an angle of 53.1 degrees. That, of course, is Mr. Graham's favorite angle, 345 right triangle. And that allows us to find a couple of things out. We can find out that the x velocity is 30 meters per second, which as a constant velocity will again stay 30 meters per second throughout. The y component of velocity starts at positive 40 meters per second, but that is going to go down by 10 meters per second every second. So it'll be 20 meters per second, then 0, then negative 20, then negative 40 after 8 seconds. We can also look at the x position, which is 0 meters to start, and goes 60 after 2, 120 after 4, 180 after 6, and 240 meters after 8 seconds. We can do the same in the y direction, 0 meters, 60 meters, 80 meters, 60, and 0, going up and then back down. The last thing to solve for is looking at the position and kind of drawing in an arc. It's a parabolic shape, as we would expect. And then we can go through and figure out the velocities, right? After 2 seconds, it's slowed down, so it's only traveling at 36 meters per second in total. At the top, it's going 30 meters per second only, then back to 36, and finally to 50. And just as we did before with the horizontal projectile, you can draw in these vectors. I first draw in all of the x components because they are constant. They don't change, 30 meters per second. But in the y direction, we start out with a big, it shrinks down, it's 0 at the top, then it gets bigger and bigger. And then finally, we can draw in the total velocities, which both change magnitude and direction as it goes. So returning to our question about the ball being tossed and thrown, right? Which of these has a longer time in the air? Well, hopefully you've realized that the only thing that really matters is the distance up and down. It could travel as fast as you want horizontally, but getting up and down is really the key here. So it's the same amount of time for both because they reach the same height. That gives it away. What is the greater initial velocity? It has to be v because it has an x component of velocity, whereas a only has a y component. And that leads us to what determines the time in the air. That is indeed the y component of the velocity. The faster it's going up, the longer it will be in the air, regardless of how fast it moves left or right. So that kind of leads us to our big idea that we use to wrap this up. We can analyze the x and y motions separately and then use time to link them, right? It's at a particular place at a particular time. The x direction motion has constant velocity. The y direction motion is free fall.